Thank you, Andy, for the introduction. Thank you, everyone, for coming. Happy to talk to you today about, holomorphic generalizations of flavour branes. So the basic idea of the talk is to introduce a family of defect operators in n=4 super Yang-Mills. And we'll be studying them at strong coupling, which means we'll be employing the ADS-CFT correspondence. And I forewarn you, this is not a CFT talk, it will be more of a supergravity talk. And my aim is to just build up a bit of intuition about how we can understand this family of defect operators from the gravity side. So what these family of solutions that we'll find, that we'll uncover, what they mean generically on the dual CFT, but it'll be more about building intuition on the gravity side. Okay, so as stated, the theory of interest is n=4 super Yang-Mills, and we'll be interested in studying at strong coupling. So the parameters on the CFT side of this correspondence are the Yang-Mills coupling and the number of colors, or the rank of the gauge group, which we can combine into the 't Hooft coupling. And we'll be interested in using the duality when it's in the form of a strong versus weak coupling. So we'll be taking lambda large while we take the string coupling to be small, which necessarily means that we take n to be very, very large. And on the gravity or string theory side, this corresponds to taking alpha prime to be very small relative to the size of the ADS geometry. So this just means that only long wavelengths can propagate in the ADS5 cross S5 geometry. So that will be replacing the string theory with its supergravity approximation. Okay, so the key player that we will start to generalize in the second part of my talk is what's known as a flavour brane. So now we have this duality. What are some of the interesting things that we can do with it? Well, one of great importance is trying to introduce matter holographically. And so the prescription for doing this was introduced in 2002 by Andreas Karch and Emmanuel Katz by employing what's known as flavour branes. So the basic idea is as follows. So we'll start off by just writing down the metric of ADS5 cross S5. And then we will write these transverse directions relative to the field theory directions in the following parameterization. In two sets of radial coordinates, one where the angular coordinate is a 3-sphere, and the second where it's just a 1-sphere. And the idea is to insert what's known as a probe brane along the directions, along all of these directions, the field theory directions here, this radial coordinate, and then the 3-sphere in the transverse directions. And what I mean by a probe brane is a brane that is very light compared to the number, or there are much fewer number of these branes as compared to the branes generating the background ADS5 cross S5, which means that the brane simply probed this background and we can study its dynamics in a fixed background. Yeah, so the D7 brane is along these directions here. And as to gain some intuition as to why this corresponds to introducing matter or a hypermultiplet into your dual field theory, let's consider the following properties of this embedding. So firstly, since it wraps all the field theory directions, it preserves the maximum Poincare symmetry. So it's a codimension 0 defect, if you like. So no Poincare symmetry or any space-time symmetries are broken. It's maximally supersymmetric, which can be understood just from flat space intuition based on the number of mutual Neumann and Dirichlet boundary conditions between the D7 brane and the background ADS5 cross S5. But if you really like, you can study the supersymmetry conditions for this, and you find that it breaks half the supersymmetries, which is the maximum number that it can preserve. But the most crucial point is that the embedding of this, or the profile of this brane, is given by a transverse radial coordinate, which essentially parameterizes the separation between this brane and then the stack of D3 branes generating this background. So pictorially, we can try and visualize this as follows. So if we imagine this plane here is just the field theory directions where we say the D3 is living. And then in general, if the brane is embedded in non-zero y, the D7 brane, then we can imagine this is sticking kind of above the stack of D3 branes. And crucially, it means that there can be string modes that stretch between the D3 and the D7. And so they have finite size, and since strings have tension, this corresponds in the world volume theory of the D3 brane as introducing something with mass. Okay, so we can spend a little more time on this. So I really want to build up some intuition for what this embedding means holographically, because a lot of the general ideas that we have here, I'll build upon later on in my talk when I start talking about holomorphic solutions. But a lot of the intuition holographically that I will use is based on this idea. So in more detail, we're inserting a probe D7 brane, which means that, so if we have label the number of D7 branes that we place into our background as NF, we want this to be much smaller than NC. So this condition can be understood both gravitationally and in the field theory side. So gravitationally, this just means that the source contributions from this D7 brane to the background equation of motion is negligible. So ADS5 cross S5 is fixed. And then in the field theory side, this corresponds to the quenched approximation, where the quarks that this is dual to, or the squarks, or the hypermultiplet this is dual to, does not contribute dynamically. So again, this is dual to the background being fixed. So the beta function in the dual field theory looks like this. In this probe approximation, this goes to 0, and this is also an important condition for the theory to be UV complete too. So it's quite important. But just out of interest, if we don't take this probe limit, then we have to consider back reaction, which is dual to, or the considerations of this back reaction is dual to there being a Landau pole here. So even when the correspondence breaks down, there's a dual understanding of it. Okay, so focusing on this picture that I drew here, the basic solution to the equation of motion of inserting this D7 brane into this background yields the solution y is a constant for the shape of the brane, which is pictorially this diagram here. And so when C is non-zero, it means that the strings stretching between the D3 and the D7 have finite size. And so this corresponds to a mass in the dual field theory for the hypermultiplets equal to, so just the tension of a string times the distance of separation. Okay. And so a little bit more motivation is how we can see that this is indeed not just based on the fact that the strings now have tension. We can understand some of the dynamic properties of this embedding in the dual field theory. So if we use a change of coordinate systems defined as following, then this embedding y is equal to constant is equivalent to and in this coordinate system, I should say that r very, very large corresponds to the UV. And so here, when we take r to be very large, theta is pi over 2. Which corresponds to the brane being fully extended over the D3. Whereas when we reach a point where r is equal to c, i.e. the scale of this separation, and also the scale of the mass in the dual field theory, corresponds to this theta going to 0. And so we see that the brane completely falls off the 3 sphere that it's wrapping, and so therefore no longer exists. And then this is due to the fact that when you like flow along an RG flow, and you reach a point where the energy is of order of the mass of your hypermultiplet, below these energy scales, you should integrate out the mass, and so it should no longer be present. And so this is basically the dual description of inserting a hypermultiplet, and it's just the motivation. So this is the basic example which I'd now like to try and generalize. So the basic type of branes that I would like to consider are essentially of this type, except we do not consider y to be a constant, but rather we allow it to vary on position. And we'll find that both supersymmetry and or the equation of motion demand that this variation behaves in a very specific way. And so in the dual field theory, this is, we'll find that this is due to a supersymmetric position-dependent mass. And in general, it will now parameterize a defect of codimension greater than 0. So more specifically, we'll make the following generalization. So to set things up, let's reconsider the metric for ADS5 cross S5 and define the following coordinates. So the following set of holomorphic coordinates. So we have x2 and x3 are 2 of the field theory directions. And then its complex conjugate. And then instead of considering a single y, we'll now consider a complex pair. And so written in this coordinate system, the metric becomes So we see that the angular part from before remains, but we've now introduced, instead of the remaining transverse directions being written in polar coordinates, we transformed it into a complex pair of variables. And similarly, to define a complex embedding function, we've transformed two of the field theory directions. Now this f I can keep general. So for all of the following, we don't necessarily need to take the near horizon limit where holography can apply. The results completely work for the asymptotically flat background generated by the D3 branes. So I just want you to keep that in mind. But for the purposes of holography, we take the near horizon limit, which just corresponds to dropping this +1. But all of the results are completely general for this more for the more general warp factor here. Okay, so in this geometry, we will consider embedding a D7 brane by essentially analogy with the constant case along the complete field theory directions, radial coordinate, and this 3-sphere. But now instead we'll turn on both the y and the y bar to describe its profile in the transverse space. And we'll make an ansatz that these transverse coordinates can depend on position. So both the complex variables and the radial direction. The motivation for doing this is that it is the most general ansatz that preserves 1+1 Poincare invariance. And so we expect in general for this to correspond to a two-dimensional defect preserving uh, 1+1 Poincare symmetry along the time and one of the field theory directions here. I'll get onto that. It depends on the embedding, but we can say for definite. Okay. So essentially depending on the profile of this embedding function, we can get points of supersymmetry enhancement, as we'll see more generically when I start to introduce these solutions. But immediately, the equations of motion and also supersymmetry demand that y does not depend on rho. So we can automatically drop this, and this is still a consistent ansatz for us to consider. Both, like if I draw the following diagram. No, well, so the vacuum will be wrapping Z, but in general, when Y is dynamical, you can imagine a non-trivial profile in the Y Z plane, which could look something like this. So we now see that the brane is leaving the Z direction in favor of the Y direction. And so the actual directions that it wraps generally are along the time and space direction. So maybe it's a little not very rigorous to call it exactly a defect along these directions, but at most, if it will be a defect, it will be along these directions. And we'll see more like a specific case where there will be an RG flow to a defect along this. But when I say defect, I mean more that it's leaving the Z plane. Yeah. Perhaps defect is too early to jump to calling it that. But for certain, these embeddings will always wrap these directions.
no longer conformally flat, or like this memory something.
Yeah. Well, whenever y is non-zero, you'll have a loss of conformal symmetry. And this is an important point for when we actually consider an example, which should make this clearer, is when you can get supersymmetry enhancement is when you hit a 0 of y. And so when the branes come together and you lose this scale, which is breaking conformal symmetry. But yeah, so what I'd like to do is try and build up some intuition of what these solutions mean as generally as possible. So when you have supersymmetry enhancement, when you can have what amount of supersymmetry is broken generically. But I'll make this clear with an example towards the end. Okie doke. Yeah, so as I said, we really shouldn't consider dependence on rho, but we did just for full generality. But we found that the equations of motion actually demand that it doesn't depend on rho, which you can also view as a constraint from supersymmetry. We also, in our ansatz, do not consider any gauge field on the brane. So the action that we want to consider simply describes the world volume of the brane. So generically, it has this form. So these are the directions of it's wrapping. So or what the vacuum should wrap. And then this is just the world volume measure. And so oh yeah, sorry. So then in this coordinate system, r becomes rho squared plus 2y bar. Yeah. So in more explicit detail, because this is punchline, this Lagrangian reads yeah, where G here is the induced metric on the brane. Induced via this embedding function. And I will just keep for f of r for brevity, but you should always keep in your mind that r here is defined as follows. So the induced metric explicitly has the following form, where we've integrated over the the angular coordinates. Now, crucially, this Lagrangian can be written in two equivalent ways. So if we define this as a Lagrangian density L, then we can write it in the following ways. And so we can deduce that the Lagrangian is bounded by the following quantity. Because all of these squares are positive, all of these terms are positive. Yeah. So the Lagrangian is bounded by this quantity here. And saturation of this bound is found exactly when y is either a holomorphic or anti-holomorphic function of z. Where I'll now define this quantity here as z. And so, in fact, this quantity, just for your to be thorough, this can be interpreted as the magnitude of a charge of the central charge of the D7 branes world volume theory, whereas both of these terms together can be considered as space-time topological charges in the ambient AdS5 cross S5. But that's getting away from the kind of point of what I want to talk about today. But this is essentially just a BPS bound, because the Lagrangian here is just minus the energy density. Okay. So, yeah, we see that the Lagrangian obeys this following bound, and so that we can reach an extrema of its action function out on holomorphic or anti-holomorphic solutions. And so one would expect that this also solves the equations of motion resulting from this, and we find this is indeed the case. So this is just essentially the Bogomolny trick. Oh, yeah, so plus corresponds to holomorphic solutions, and the minus when you have an anti-holomorphic. So when this term is 0 is when you have an anti-holomorphic solution, which gives you the minus, and then similarly for the holomorphic. Yeah, so I mean, do you mean picking another pair of coordinates? Yeah, so there's more to be said about like these coordinates were chosen at random. And so there are different generalizations you can consider, and one of the generalizations that maybe I'll get to later is you can consider these coordinates plus light cone coordinates in the remaining two directions, or you could consider any number of these permutations of coordinates. And so some further work we've been doing is trying to consider what the most general type of complex coordinate system one can consider and still produce these. But yes, you're absolutely right. But I'm starting off with just the most simple case to illustrate the idea. But it's very general, as we'll see, hopefully. Okay, so since this is a BPS bound, we should expect that this implies that holomorphic and anti-holomorphic embeddings preserve some supersymmetry. And indeed they do. So without going into the specifics of the actual calculation to show that this is supersymmetric, I'd like to keep things more general. The idea being is to build up an intuition about what these terms mean and their generalizations when they appear in the Lagrangian and how they translate to supersymmetry conditions. So what I'd like to do is go through the general idea of how we can find supersymmetry for D-branes, which is this story known as kappa symmetry. So if one wants to know whether a certain brane action given by a particular type of embedding is supersymmetric, one way that we can do this, and the canonical way of doing this, is promoting all of these world volume fields to superfields, and then constructing a manifestly supersymmetric action out of these quantities. This is essentially just the superfield formalism for branes. And so from this quantity, one can construct a supercovariant action. But we see that we've introduced some additional unphysical fermionic degrees of freedom. So one of the constraints physically for our supercovariant action should be that there should exist a symmetry that allows us to gauge away these fermionic degrees of freedom. And this symmetry is known as kappa symmetry. And so in combination with the usual supersymmetry transformations acting on this superfield Z, we also have a additional kappa symmetry. And so the general variation of our fermionic degrees of freedom will look like this. So this here is the kappa transformation. Plus some regular supersymmetry transformation where this here is a Killing spinor of the background. And so some important things so this projection operator here, gamma, or so this quantity is the projection operator, but this kappa operator, kappa projector, what it looks like is embedding specific. But its important properties are the following. It squares to 1, and it's traceless and Hermitian. So as mentioned, we'd like to gauge away the extra degrees of freedom here. And it turns out, by just counting what the additional degrees of freedom are, that there are twice as many degrees of freedom as physically necessary or physically required. And so in general, one imposes a gauge like this, where P is any projection operator. And so then the remaining transformations which keep us in this gauge correspond to the following requirement for the transformation of these fermionic coordinates in this gauge. rank of the projection operator? P.
You say it's a projection operator?
Yes. So we require that P squared equals P. No, in general, you just want any operator that eliminates half the degrees of freedom.
Yeah, that's what I meant. Half rank then.
Yeah, yeah.
Okay.
Okay, yeah. yeah, exactly. So we require this to be equal to 0 to remain in our gauge and also have supersymmetry. And this is equivalent to the following condition, which can be found by multiplying the left-hand side of this by this operator here. And so this is the key identity that preserved supersymmetries must obey. Where this gamma is this embedding specific projection operator, and epsilon is, so the rank of epsilon need not be half, as we'll see, it can be more than half. The rank of gamma, rather. And its rank determines the preserved supersymmetry, essentially. Yeah, so this is the key condition. So the whole point of introducing these kind of verbose technical details are essentially just so I can relate this back to the BPS condition we had for the Lagrangian. And I can do this as follows. So what we can do is that we can take the product of this with its complex conjugate, and using the hermiticity property of gamma, and these properties here. It's equal to 0. In fact, this is greater than or equal to 0 because this is manifestly positive because we've constructed an absolute value of this spinor quantity. And so this evaluates to, and if we choose a normalization for our spinors such that they are equal to 1, their magnitude is equal to 1, then we get the following bound, which is saturated when we have supersymmetry. Okay. And it turns out this bound is exactly the bound we have here. And so when this is saturated, we also have supersymmetry. And so for our specific embedding, I said that gamma was embedding specific. It takes the following form. Where these are Dirac matrices, curved space Dirac matrices that have been pulled back to the brain. So these are the induced gamma matrices on the brain. And so if we now insert this into this inequality here, we can multiply out by this square root of the determinant. So we get the following inequality. Which is actually an inequality of this form here. So this bound is essentially a bound for supersymmetry, is the point that I would like to make. And what I'd like to argue is that interpreting what these two terms on the right-hand side mean in correspondence with this condition here, you can read off essentially how much supersymmetry is preserved. Because a number of independent conditions you have here that the killing spinners need to satisfy is in one-to-one correspondence with the terms that you have here. So actually going through the kappa symmetry calculation for our specific embedding leads to the following conditions that the killing spinner needs to obey. Where this plus is for holomorphic embeddings, and then this is for anti-holomorphic embeddings. So we find that there are two independent conditions, and so supersymmetry has been reduced by a factor of 4. And so this is relative to all the superconformal generators haven't broken based on the point raised earlier. So of the remaining generators, these have been reduced by a factor of 4, which means that in general, 4 supercharges remain unbroken. Okay. So what can we say about the chirality of these supercharges? Remember, this is completely general. So this is for any holomorphic embedding that we consider generically, apart from the issue of supersymmetry enhancement, which we'll get to in a second. At minimum, we have 4 preserved supercharges for holomorphic embeddings, or anti-holomorphic embeddings. So the relevant 2D chirality operator that we want to consider is the one along the time and additional field theory direction. So it looks like this. And bearing in mind that the killing spinners of the ADS5 cross S5 background need to obey the following condition, which notice the similarity between these here. Then we can deduce the following. Using that our preserved killing spinners will be eigenvalues of the following operator. We can show that this is equal to which, using a property of all of the background's killing spinners, because they're coming from the background geometry, we know that these are equal to plus or minus epsilon. So for holomorphic embeddings, we have spinners of positive chirality, and then for anti-holomorphic embeddings, we have spinners of a negative chirality. So in general, we then have the following preserved supercharges, 4, 0, supersymmetry, and 0. So this is the 2D preserved supersymmetry for holomorphic embeddings, and then 0,4 for anti-holomorphic embedding. Oh, yeah. Yeah, so this is where this chirality operator is coming from as well. So this is the chirality with respect to the 0 and 1 directions. Yeah, so generically they'll have SO4. Yeah, and so that's in one-to-one correspondence with when if the brane then flows to a point where it's fully wrapping the S5, you get supersymmetry changes, and in correspondence the R symmetry changes. And similarly, if Y goes to 0, you get some enhancement too. But yeah, so in general you have, let me think about this actually. Yeah. Okay. So I'd like to now start talking about points where you can have supersymmetry enhancement, which essentially corresponds to points along the brane's embedding where one of these conditions drops out. And so my hope is that I built some intuition behind, or what I'd like to now do is build some intuition behind these conditions for the killing spinner and these quantities that appear here. And so if we can find conditions when one of these terms dominates over the other, then this should correspond to one of these terms vanishing in the kappa symmetry calculation. Finished. Okay, so because this is type 2, B, supergravity, then we know that the killing spinners have the same chirality. So now this is the 10-dimensional chirality operator. So the killing spinners also obey this condition. Now, if we multiply these operators up here by this, then we get out the following equivalent projection conditions. Which, if we compare it to this condition I wrote at the bottom left here for the background, these are essentially flat space supersymmetry conditions for the following branes. This is the background E3. This is for a D7 brane wrapped completely along these directions indexed here, where maybe I should just define this as follows. So these are 1, 2, 3, 4, 5, 6 to 8, and then 0, 1, 2, 3, 4, 5 to 7, 8, 9. So this is for a D7 brane wrapped along the Y and Y bar instead of the Z and Z bar directions. And then this is for a D7 along Z and Z bar directions. And so what this embedding, what this division of the Lagrangian is telling us is that this is a term corresponding to a brane along Z and Z bar directions, and then this along Y and Y bar directions, which we can see by writing what these terms are explicitly, including measures. So if we reintroduce measures to this Lagrangian, then we find that the action looks like this. Which we can separate this term is just the action for a vacuum D7 brane along the Z and Z bar directions. So if you turned Y off, this is what you'd get. So then this we can view as a brane, the contribution from a brane along the Z and Z bar directions. This quantity here is a measure going from the Z coordinates to the Y coordinates. So we could alternatively write this let me do D6, DZ, DZ bar, rho cubed, plus or minus D6, dy, dy bar, over f squared. And this is now the Lagrangian for a brane just embedded along the Y directions if you didn't turn any Z direction on. And so I'm trying to convince you that these supersymmetry conditions and the bound that I wrote earlier from the kappa symmetry really does mean correspond to the quantities we see in the Lagrangian. And so if you believe that, then it stands to reason that if we can find limits where one of these terms contributes more than the other, this should correspond to one of these kappa symmetry conditions disappearing, and so we should have an enhancement of supersymmetry. So let's ask what these conditions are. And I should say that, okay, the intricacies of what special points exist depend on the specifics of your embedding. What I'm trying to do is keep things general. So what are the general properties of these embeddings? Yeah. Mm-hmm. You are. Yeah, no, you are. And this is the preserved amount of supersymmetry along the defect.
Introducing the defect, you are breaking the space-time symmetry.
Yeah.
And you're also breaking supersymmetry.
Yeah. Yeah. So what you can understand is how I like to think of holography is that you're really geometrizing everything that's happening in the dual field theory. So we understand that these conditions, why they're coming about from the intersection of branes essentially, and so when you have branes intersecting, there are some symmetries that are broken because the topology changes, only a certain number of supercharges are preserved, essentially because you have extended objects in your ambient space, in your ADS5 cross S5. And then this descends down when looking at things just from like the world volume theory of the D3 into these conditions here. But you can, the point in holography is that you're viewing these things geometrically and then interpreting what they mean in the CFD. And so this is what we should learn, is that generically these embeddings are dual to two-dimensional defects that preserve the corresponding supersymmetries, these supersymmetries.
Why break that two-dimensional zero in the x0 and x1 directions? In those directions, if you like anti-commute the supercharges, you'll have supercharges that anti-commute the momentum. If you broke into once in the x2 and x3 direction, transverse. Yeah. It's weird, but yes. If you break momentum,
Yeah.
supercharge square gives that momentum.
Yeah, that's exactly the right intuition. Yeah, and so going back to this diagram that I drew earlier for if this is the D3, what Andy was saying, this is what the constant Y embedding looks like, where we have Y constant. There is no defect along the D3's perspective because the brane is sitting above it. The D7 brane is sitting above it, so the full Poincare symmetry is preserved, which was the why this corresponds to a hypermultiplet. But when you start considering non-trivial embeddings, you can have like the Y may sink down to the D3, and then it's like from the D3's point of view, we've introduced a defect along this world. Sorry, my skills as an artist are lacking. But you can imagine this brane like now sinking down towards the D3. And so the point now I'd like to make is that, okay, so this is maybe a visual tool to help understand where you get some supersymmetry enhancement. So we mentioned earlier that is at the very beginning when Y is constant, you break superconformal symmetry. If this C goes to 0, then you get superconformal symmetry is restored. So we might hope that something similar happens if you zoom in on this part of the geometry, you get something that looks similar to, obviously the full geometry, the supersymmetry won't be restored because it's a defect, but you can have something similar going on where there's some SUSY enhancement, which is exactly the point that I want to make here, is that when one of these terms grows relative to the other, corresponds to zooming into a particular part of the defect and corresponds to some supersymmetry enhancement. Be it the defect is no longer present, or that you only have the defect. But I'll try and be a bit more specific now. Okay, let's make a table. So if I label these as the action for a brane along the Z and Z bar directions, and then this for the action of a brane along the Y and Y bar directions, we can ask ourselves, when do one of these terms dominate over the other generically? Well, we see for this case, this happens when this warp factor goes to infinity. So when this is killed off. And this, remember that we're defining f as r squared over L squared equals rho squared plus 2yy bar. In fact, that's not necessary. We can look at that in an example. This, yeah, so when f, so this is how we're defining f. So generically, this happens when r goes to infinity. So this is in the UV. And so this corresponds to essentially something like the flat case, where the defect, so the brane along the y and y bar directions is ignored, and you have something just along the z and z bar directions, and so the presence of the defect is now ignored. On the flip side, this term dominates when f of r goes to 0, which comes about in the IR, generically. Yeah. So this is all. So I wanted to keep things in the near horizon limit, just for like holographic purposes. But there's a. Well, yeah. So no. So that holds up to the story of. So the generic f. So now we're talking about purely the near horizon, but everything prior to this holds for generic f. But the interpretations of supersymmetry enhancement, when you have this +1, it's not necessarily true that this holds. So this is just in the, and I wouldn't be identifying R with the UV and IR in that case as well. So this is now just for holographic purposes, and so understanding what happens to this defect as we. So this is generically true for for functions that have no poles and just zeros. But the this is true for any multiplicity, for a y that has any zero of any multiplicity. Poles are a little more tricky to consider, and I don't think we have like a clear picture on what really to do with them. Yeah. Yeah, this was just, sorry, so that's probably a bad example. It's just to illustrate that. So you could view it as something like this. So maybe the picture I drew before could occur to something like, this is probably a more accurate picture that I should draw, which would correspond to something like this. But I just wanted to illustrate the, you can have poles. Yeah. So you can have poles. We're just a little unsure about what the interpretation of these of when you have a pole is. But certainly when you have a function, a more simple function that just has zeros of any multiplicity, then there is a clear interpretation, and this is the understanding as we, if you like, yeah. But no, but yeah.
As long as it's holomorphic, it solves the equations in motion and preserves that. If it folds, then you have to do something.
There is a more geometrical story behind this as explaining why these functions should be holomorphic, which pertains to something called calibrated geometry, which is essentially a requirement that you have on a manifold that the brane should wrap to preserve supersymmetry, but which is essentially this relation between the kappa symmetry and these actions that I've shown here. So holomorphicity is a requirement that can be seen for those kind of studies, but it's it's far more involved than the stuff here. I just want to keep it at the level of the equations of motion. So this is true.
Square root of c squared minus 1 allowed.
Yeah.
Then you can
So square root of c squared minus 1. So where we're at now, the issues of branch cuts, we interpret as there being multiple branes. So if you have, so say if we take, I don't know, z to the n, then this has the interpretation of there being n branes extending along the, in n branes of this type. So each of the branches you can sort of think of as corresponding to a different brane. So this is the kind of interpretation that you should, so I think there is quite a clear geometric interpretation as when you have multi-valuedness. It's not just a weird thing that you don't know how to interpret. It should be interpreted as there being, actually the different sheets are different branes in this story. Yeah, so this is what I mean by case. There are weird things that could happen. This is just, because the power of this, that there's a whole family of these solutions which you could study in detail and you could pick your favorite and then analyze its properties. I'm just trying to highlight what generic properties happen, specifically at special points along the RGE flow that are kind of generic. But you could cook up an example where, you know, strange things happen, but in principle, they're why? Yeah, I was trying to think of a way of organizing this in a way that presented what I trying to think what the generic properties are of these embeddings are, but they're so generic as to being hard to kind of categorize. No, it's okay. Yeah. Okay, so yeah. So up to these implicit assumptions that I've made, what is the SUSY enhancement of these points? So in this case, this is essentially what leads to the case we were discussing here when Andy mentioned the y equals constant embedding, is that when this happens, we essentially ignore the presence of the defect and our 2D symmetry is enhanced to a 4D supersymmetry because now the brane extends along the complete Z and Z bar directions and there is no defect along the D3. And so this is akin to dropping this condition here. So we've lost a term in the Lagrangian, and correspondingly, we've lost a supersymmetry condition. And so the brane starts off now life in the UV as completely extended without any defect. In this case, we get an enhancement of 2D supersymmetry because essentially we just care about the y and y bar brane because it dominates over the contribution from the Z and Z bar brane. And so this amounts to dropping this condition. And so we have a doubling of supersymmetry. So 4, 0 goes to 8, 0, and 0, 4 goes to 8, 4 as a generic property for these types of solutions. To 4, 4. Because the branes still have, this was the condition that determined the chirality of the brane, of the embedding, and this is non-zero, so it's still using this argument that we had earlier. These will have definite chirality along the 0, 1 direction, along the 0 and 1 direction. So this was this in tandem with the 2D chirality operator is what we are using to determine the chirality of these. Yeah. Yeah. Mm-hmm. Yeah, I'm not sure. But so these are. Yeah. So, but this just comes down to this condition here. So this is the check that we're using, and this. Yeah, so this is for holomorphic, so this is plus or minus. So the plus is for holomorphic and the minus is for anti-holomorphic. Yeah, so I dropped a plus. So this condition remains. This, yeah, so in this limit, this condition remains, and this is what we're using to determine the 2D chirality. So holomorphicity and anti-holomorphicity still exists, and correspondingly, there is still a definite 2D chirality is the interpretation that we have. I mean, if you would expect then, if that were to be true, then these killing spinners not to be eigenvalues of this operator. But this logic and the fact that they're background killing spinners says that they are. I'm not sure how you would check other than like using like the two-dimensional chirality operator. You'd expect it to not be an eigenvalue, like to be to not be an eigenvalue of this equation if it was 4, 4. But yeah, maybe because so the fact that they are background killing spinners of the 2B, is it? It's certainly it's true that this is in part coming from the fact that they're in a background generated by D3 branes, because the condition that the killing spinners have to obey is part of what we use to argue their chiralities, and that we combine these and then you get the projection operator for the background killing spinners. So maybe it is coming from. Okay. So let's try and make things a bit more concrete by considering an example. So we started off by motivating these generalizations by considering the known example of, which has been mentioned a few times, the y equals constant. The most simple generalization of this that you could think of is just y is a linear function. And importantly, because the dimensions of y and z are equal, this constant c does not introduce any additional scale into the theory. So it is the only solution that could possibly give you a restoration of conformal symmetry. For higher polynomials, c has to have a dimension, and so there's no way that you're going to get conformal symmetry back. But for the linear solution, we'll see that we can. Okay, so if we insert this into this warp factor, that in the near horizon limit, again, just so everything pertains to holography, then we get And so based on these arguments here, we see that when r goes to 0 corresponds to rho going to 0 and z bar going to 0. And so in this point, we get supersymmetry enhancement from 4, 0 to 8, 0 and 0, 4 to 8, 0. And we can ask whether conformal symmetry is restored at this point by studying what the induced metric looks like. So this is, we're zooming in, did I rub it off? We're zooming into the geometry kind of in this region here. And we're asking, what does the physics locally look like at this point? Or how does it behave? And so the induced metric on the brane in this limit explicitly reads on this solution. I'm just going to keep this as in terms of r, just so I can write this a bit quicker. Plus, oh. Okay, and so if we take r to 0, the metric becomes the following. Which is the metric for ADS3 cross S5. And so now we have a restoration of conformal symmetry. So alongside these 8, 0 and I've written 8, 0 twice there. We now also have some superconformal generators in the IR. So this embedding corresponds to a defect that flows to an embedding that flows to a superconformal defect in the IR. Okay, so that's a specific example of these types of embedding. But as we were discussing a moment ago, you could cook up other types of examples which have different special points where there may be supersymmetry enhancement at different points along in the Z and Z bar plane. I don't have a lot of time to talk about further generalizations of this, so maybe I'll just write a few things down. But the point that I'd like to make is that this is quite general. You can consider different combinations of coordinates, more than one set of holomorphic coordinates. All of these satisfy the equation of motion. And this can apply in different space-times, so in different holographic systems. The condition, so let me first try and, yeah.
Translationally invariant in x0 and x1. Then I can let my mass depend on the effect of a linear dependence. And at the point where the mass goes to 0, which is okay.
Now rub it off again. Oh no, this one here. Yeah. But in general, for different types of embeddings, you won't get something that has this nice geometry, and so you won't get there won't in general be a restoration of conformal symmetry as well. No, because the multiplicities kind of spoil things. So if you take, possibly, I think that might be, yeah, any linear zero, I think this, because I think that would be the minimum requirement for you to, so as long as you're not introducing any scale, then I think at any zero you should have a restoration of conformal symmetry. So I think you could argue that, yeah. Yeah, yeah. Yeah, so there may be some other generalities that I've missed. These are just the ones that I could think of. But you can play some games and try and think about what other generic features of these embeddings exist, which is kind of the power of their existence. Okay, so I won't discuss generalizations to other spacetimes, but I'll quickly just say what you can do in this, how you can generalize this type of embedding. So instead of z and z bar, you could take light cone coordinates of the field theory directions. And exactly the same story goes through, except the Lagrangian now reduces to, we get the following bound on the Lagrangian. You could equally Wick rotate the y to get this in kind of light cone coordinates for the y as well. Which is 1 plus or minus a new charge, x, instead of z. So now we have the base brane along the z and z bar directions, and now a brane that is no longer extended along the t and x directions, but is along the y and y bar. And so you get, this corresponds to the following supersymmetry conditions. And hopefully the point of introducing the kappa symmetry was so that I can just now state what the supersymmetry conditions are and you believe me. But you can work it through, and it is true. These correspond to the following supersymmetry conditions. So this for the z and z bar. And then this for the y and y bar, now no longer along the t and x directions. So this corresponds to the one along t and x, and this doesn't. We can now also consider combinations of light cone coordinates and z bar, and you get a Lagrangian that looks like 1 plus or minus z plus or minus x. And you now get more breaking of supersymmetry. So we have this further condition. And in all of these cases, you could consider different points where maybe one of these vanishes, both of these vanishes. So there are different games where you get supersymmetry enhancements at different points along the field theory directions. But the point is that really any function, and so the solutions that saturate this bound now are those that lie along one of the light cone directions. So we can have x plus z, x plus z bar, etc., etc. And all of these are valid functions that preserve supersymmetry and solve the equation of motion. Okay, so I'll probably end there. The final comment that I'd like to make is that, as I briefly mentioned, this extends to other holographic backgrounds and other supergravity backgrounds as well. There are a couple of conditions about the type of branes that you can embed that preserve supersymmetry, but I don't have time to go through that argument. Yeah, so I'll finish there. Yeah, so well, these would be defects along the Z and Z bar, and then yeah, they raise up along these like cone groups. Yeah, I'm not really sure what the combination would correspond to.
Preserve supersymmetry.
Yeah. It would be like, I think it would be like a lattice of these two types of defects, I think, and then some combination of the supercharges is preserved. And then if you zoom in along one of the defects, you remove either this condition or this condition, and you get 0, 4 or 4, 0, or whatever the supercharges that appear when you get rid of this condition. Yeah, so we've essentially just transformed from Z to Y. And in this, when you're approaching Z goes to 0, the geometry actually looks like the branes wrapped along the fully wrapped along the Y in my bar direction, so it's fully along the transverse direction.
Then in order to avoid this singularity, maybe you can go to Y coordinate instead of Z. With that,
So what have we done? So we verified that, okay, if you do, as you're saying, swap, if you now pick a brane along the Y and Y bar directions and consider a Z of Y embedding function, then similarly, holomorphic functions for Z of Y exist. And then you're saying that this corresponds to, yeah, so I think that, then we did find that meromorphic solutions are solutions to the equations of motion. And so then that would agree with it if you just have a holomorphic solution for Y. Yeah, so that is true. So yeah, so I mean, you could, all of this, again, there's a consistent narrative here if you started from any number of these branes and considered different embedding functions, as you're saying, and all of it is continually true.